So good evening, and thank you very much to everyone who's joining us this evening. And I'd also like to thank the Royal Society of Chemistry, the West Midlands Chemistry Teaching Centre, and the University of Birmingham as well for enabling these lectures. We've had some really interesting talks so far as well on practical application, industrial application of chemistry. But of course, as exams draw near, we're thinking about revision lectures. And some of you may recall that we have several topics, but one of our more popular ones, and certainly the registration has shown it to be very popular, is my good friend and colleague, Dr. Peter Hoare from Newcastle University, who's the STEM outreach officer there. And normally you'll see him in person giving these demonstrations and lectures. And as you said before, we're looking forward to when we can sort of come back and have those live demonstrations. But we have got the next best thing, which is Peter's very kindly filmed some of these, and I won't steal his thunder, but he has put them in his PowerPoint presentation. So we will at least see some of the color changes that he'll be discussing as well. So tonight's topic from Peter is a revision lecture on transition metal chemistry. And are you going to mention electrochemistry, Peter, or is it just the transition metal?
No, just transition. It'll be a bit of redox. Yeah.
Yeah. Brilliant. Great. Well, thank you very much once again to Dr. Peter Hoare from Newcastle University. And without further ado, I'd like to invite Peter to share his screen. And whilst he's doing that, I'll just remind people that if you would like to ask a question, please put your question in the chat. And at the end of the lecture, then we'll read some of these questions out, and Peter will answer them from there. So thank you very much, and over to you, Peter.
Thank you, Mark. Just checking you can see my PowerPoint slide there.
Yep, all looking good. Brilliant.
Thank you very much. Well, thanks very much for that introduction yet again, Mark. And it's great to be with everyone, if only virtually. So as Mark says, I work at Newcastle University. You can see that on the slide. Well, I'm a STEM outreach officer. I've worked here for 14 years. Before that, though, I was a chemistry teacher. I used to teach chemistry in a Northumberland high school for 20 years. And I'm also probably more relevant for this session. I'm an A-level examiner, a marker for AQA, obviously one of the main exam boards. I've been doing that since 1995, so rather a long time now. So I've been involved in teaching and sort of marking chemistry A-level for well over 30 years. So as Mark said, this session is going to be on transition metals. We picked this topic because it's one of the ones that's sort of high priority when we got the list from the exam boards on what some of the longer structure questions are going to be. Transition metals was one of the topics right up there. So we thought rather useful to do this lecture. I've given it before in Birmingham face to face. In fact, it's the first revision lecture I did in Birmingham, I think about 4 or 5 years ago now. But here's the online version. So there will be some demonstrations, but as Mark says, I've pre-recorded them. So I'll just give a little plug for my colleague Mackham guy. If you've never heard of him, he's a guy called James Donkin. He's head of chemistry at Hartlepool Sixth Form College in the Northeast. Well known to a lot of students and teachers through his YouTube channel called Mackham Guy. It's a play on words. He's from Sunderland. Someone from Sunderland is called a Mackham, but he's also a chemist. So there we go. I can thoroughly recommend James's YouTube channel. He's got hundreds of videos covering all topics across the whole of A-level chemistry. He teaches OCR, but the topics will cover everything: OCR, AQA, EdXL, most of the major exam boards. And so I can thoroughly recommend James's YouTube channel too. The little video clips. He originally just made them for his students just as revision. They then started passing them on to friends. So he put them on a YouTube channel and they're available for everybody, completely free of charge. Okay, so this session is going to be interactive. I'm going to be asking you some questions that you'll vote for the answers using some sort of mobile or any device that's got internet access. Basically, I'm using my mobile phone just to check it's working. But that's the login, ra.ombia.com, and the session ID is PH10. I'd like it to be PH1, but I have to have two letters and 2 numbers apparently, so it's going to be a bit alkaline this evening. I'm usually quite acidic, so I prefer to be PH1. But there you go. That's another comment, of course. My name is just Peter Hoare. I don't have a middle name. So what else could I be but a chemist with initials PH? And there we are. And those of you who follow me on Twitter will see I've got 2 variations of that, but enough said. So if you get yourselves logged in, there'll be a test question in a moment just to test if the system's working and you're all logged in. I'm just going to wait for the majority of people to vote because one of the things that Ombia doesn't tell me is how many people have registered to vote. So I'll just wait until the counter stops going up rapidly. I can't tell how many people have registered. And it's good that still people joining the session. That's excellent. So that's what it should look like. That's what it looks like on my mobile phone. It's just saying waiting for the poll to open. So let's have a test question then, just to see if OMBI is working. And because we're doing transition metals, my test question is a transition metal question. Which one of those then is the best definition of a transition metal for A level? You notice there's a little green box in the corner of the screen. I think you guys should be able to see it as well. And it's counting up with how many people have voted. Notice the question appears on whatever device you're using, phone, tablet, laptop, whatever. You can click on whatever you think the correct answer is. You can also change your mind as well, by the way, with this system. As long as polling is open, that green box is lit up in the top right-hand corner. You can change your mind. You're not committed to your first answer. It's the last button, the last answer you record before I close polling is the one that appears on the system. This is completely anonymous, by the way. I've not asked for anybody's name. When you logged into OMBI, it's done anonymously. All you'll see on the screen is a bar chart with how many people voted for each option. You'll never see any individual student responses. And this system, of course, is brilliant for doing something like this, where we're all around the country or wherever. We actually use it face-to-face with our students in undergraduate lectures where we're all in the same room, but it's also, because it's a web-based system, brilliant for online. So you stuck around 130, so I've closed polling. I have to wait a few seconds for the results to zap through from the OMBI server, or wherever it is. And okay, vast majority of you gone for answer 3, and that's a good start. That is the correct answer. All of those are indeed properties of transition metals, but the definition absolutely correct. Incomplete D sublevels, D subshells in either the element or one or more of its ions. Excellent. Let's now crack on with some chemistry, some transition metal revision, and quite a few other OMBI questions will appear as we go through. So, just me being a bit nosy, which A-level spec are you doing? This session is quite generic. I run full-day revision workshops around the country and on our campus over the Easter holidays and so on. And even though I'm an AQA marker, the sessions are all completely generic. They cover every board. And the notes booklet I give out, the notes booklet you've got today, the PDF, you will notice some of the aqueous chemistry, the transition metals is different between the boards. And so you will find there's a summary page of AQA reactions, there's a separate summary page of OCR reactions, there's a separate summary page of WJEC reactions, in case we haven't got anybody from Wales. And I think we've got the CCA one in case anyone's joined us from Northern Ireland. Only place anyone won't join us from is Scotland, because of course Scotland do not do A levels, they do hires and advanced hires instead. Okay, that seems to be the most of you. I'm just waiting for the majority of people to vote. This is just me being a bit nosy about which board you do. Vast majority AQA, that's good, you can stay. No, you're all very, very welcome wherever you've come from today. We've got 20 OCRA. I mean, AQA and OCRA are the two most common boards. They've both got about 35% of all A-level entries in England for chemistry. Excellent, let's crack on with transition metals then. So just to remind you, there's a periodic table. If you were physically in Birmingham altogether, I'd have given you one of these to take away. This is our current sort of university periodic table that we give to our undergrads, and I use a lot on outreach and so on. And we're talking about the first row of the transition metals. So I put a little red box around them there. Scandium to zinc. We don't look at all of them. We only look at selected chemistry of selected elements. When I started teaching back in the late 1980s, we used to go across that row and do some of the chemistry of every element in the first row of the transition metals. Don't do that anymore. We just do some selected stuff to sort of exemplify particular things. But that's what we're going to concentrate on. So we know the definition. We just talked about that. Notice at the end of my definition there, I've put OWTTE. That means all words to that effect. You may well have seen that in a mark scheme from the exam board. It means you don't need a word perfect definition. You just need to get the gist of it right. So there's a lot of ways you can tell me that information without writing exactly those words in exactly that order. So that's what OWTTE means, all words to that effect. So electron configurations, of course, first thing to start with transition metals, often start a question with this. And of course, we're talking about the first row. So they all start AR 4s2. And then however many 3Ds they've got. So we do fill the 4s orbital first. It's slightly lower energy than the 3D. It's the first two that get out of sequence, isn't it, when we're filling up subshells. But of course, when you ionize them, you lose the 4s first. So even though we filled 3D last, 3D is higher than 4s. When we ionize, the 4s come out first. So a little tip for you here. There's often A level's often not very black and white. It's often grey, isn't it? We often say, here's the rule, but, or here's the rule, except. This one doesn't have any exceptions. No transition metal ions ever have 4 s electrons. So if you write the electron structure of a transition metal ion and you put 4 s electrons in it, I can guarantee it's wrong. So there's no exceptions to that rule. No transition metal ions have 4 s electrons. So the next couple of questions are going to be to ask you to work out some electron arrangements. So hopefully you've got access, I should have said at the start, you need access to a periodic table because of course you need to know the atomic numbers, or you can work it out from the periodic table. So that's what they should be, shouldn't they? D1 to D10, because there's 10 of them. So scandium should be 4s2 3d1 across to zinc, which is 4s2 3d10. But as you probably know, there are a couple of exceptions. And guess what, of course, they'll ask you about in the exam? The exceptions. So here's your first question. Which one of those is the correct electron configuration of? I think it's vanadium. I can't see because the the share bar is in the way of my top of my PowerPoint. I'll just work out how to get rid of that. Okay. Oh, we've still got people trailing in. Cool. So say if you've got access to a periodic table, you'll find that quite useful. That's not working. So remember, as I said, with Ombi, you're not committed to your first answer. You can change your mind whilst polling is open. And of course, whichever option you click, it tells you on your screen which option or options. We might find some questions later on that have more than one correct answer. It's up to me how I set these questions up. There can be up to 10 answers because you've got, buttons 1 to 10, as it were. And I can decide how many are right or wrong. So it's quite a powerful system. It's not just limited to 4 and 1 correct answer, but I keep it in a format of 4 because that's what I have in exams. In fact, for years, I've always used multiple choice questions in these revision workshops. There weren't multiple choice questions on A level for a number of years. In the latest revision a few years ago, they brought multiple choice questions back on. So at least we're now practicing questions that you're quite likely will get questions of this format on the exam. The multiple choices back on A level. We had quite a long time where there were no multiple choice questions at all. I use this with our undergrads and say, sorry, you don't get any multiple choice questions in undergraduate university exams. You have to write the answers. Okay, that's most of you. Let's see what you've come up with. And almost everybody's gone for answer 2. Of course it is. It's the third one along, so it's going to be 3D3. What about whatever that one says? I think it's chromium. I can't see the top of my slide. I'll get rid of this bar. It's better. Hide floating meeting controls. I don't need them. That's better. It is chromium. I thought it was. What's the electron configuration of chromium? The element. Shall vote as well. Just check the system's working. Hope I get the right answer. Again, don't worry if you can't connect to Ombia. You've only got one mobile device. You don't have to keep flipping between windows. Absolutely fine. This is completely optional. So I don't save any of this data or do anything with it. You can clearly see it's completely anonymous. Just doing it just to make the lecture a bit more interactive than just me talking for an hour, which would bore me silly, never mind you. Okay, that's 130 odd again. Oh, thought I pressed close polling, obviously didn't. Still haven't. Oh, that's better. There we go. Oh, right. So we've got a split here now. So a slight majority have gone for option 3, but almost an equal number of you have gone for option 2. Well, this is going to bring out a very good point then, because the correct answer is 3. Well done, 71 of you. Chromium's one of the 2 exceptions. If you look on the periodic table, it might appear to be 4s2 3d4 if you count along, because it's sort of the 4th element along, but d4 has a spare empty d orbital, and by making it d5, by shifting one of the 4s's into 3d, you produce a more stable configuration. There's something particularly stable about D5. There's something particularly stable about D10. So if they can shift one electron to become D5 rather than D4, or for D9 to be D10, that is a more stable configuration. You don't need to know why. I've long forgotten why, to be honest. I must have learnt as an undergrad, but there we go. So chromium is one of the exceptions. It's 4s1 3d5. It's not 4s2 3d4. Next one then, I think this is iron 2, isn't it? I've got the floating the menu bars drop down in front of, I can't see the titles at the top, but when I muted it, it stopped my mouse working. That's why I couldn't close that question for ages. So I'll just have to put up with it and try and remember what the question was. I'm pretty sure this is FE2+. Yes, it is. Well, I just need to look at the Ombia question on my phone, don't I? Duh. Right, there we go. Oh, still got people trickling in. Evening all. Very welcome, wherever you are. We're up to 120 plus. Oh, so he jumped up to 130 there. Let's see. Right, vast majority have gone for 4. That is indeed the correct answer. If you account along iron, the element is 4s2 3d6. So when you go to 2 plus, it's going to lose the 2 4s electrons and just be d6. Of course, iron 3 would lose another one, and that would be d5. And as you all probably know, iron 3 is more stable than iron 2, because iron 3 is d5, iron 2 is d6. In fact, iron 2 solutions, they're pale green, actually oxidize to brown iron 3. That's a bit of chemistry that most of you probably need to know, because iron 3, more stable configuration, it's d5. And finally, copper 2 plus. First transition metal ions you probably ever meet, because you probably make copper sulfate in year 7 or year 8 when you were doing acids and bases, long time ago now, but it's often the first example you do in secondary school of making a salt, because it's one of the few you can easily make that isn't horribly toxic, that's got I'm still here, sorry, it's just these our university's too energy efficient. There we go. And clearly, just me talking and waving my arms about is not enough to keep the sensors active for the lights in the lab. So if I get plunged into, I'll probably get plunged into. I've been in here about 45 minutes. I might get plunged into darkness again before the end of the session. Let's wait and see. So I'm actually presenting to you from the university. I'm actually on campus, so I don't trust my home Wi-Fi. I'm actually in our chemistry PGCE lab, the lab that we use to train our trainee teachers. Okay, let's see what we've come up with. Most of you have gone for number 3, and yeah, it is indeed 3, not D9. So remember, copper's the other exception to the ground state. It's 4s1 3d10, but you lose the 1s and you lose one of the Ds, so it's 3d9. And that's of course why copper 2 is a transition metal and it's coloured. It's incomplete D shell. Excellent. So just to remind you there, and there's the 2 exceptions highlighted in red. Chromium is not D, there isn't an element that's D4. Chromium is 4s1 3d5. Copper is 4s1 3d10. Because there's something special, as we said, about D5 and D10. Okay, let's just summarize that then. They all start 4s2, fill 4s, then 3d. When you ionize them, get rid of the 4s first, and remember the 2 exceptions, copper and chromium. Annoyingly, you can't just remember it's the 2 beginning with C, because there's also cobalt on that row that also begins with C. They're not the only 2 elements beginning in C. You just need to remember, learn that it's chromium and copper that are the 2 exceptions. Okay, just to mention something briefly about oxidation numbers or oxidation states. We'll look at a bit of a redox a little bit later in the presentation, but students often used to ask me, how do I know if the oxidation state or the oxidation number is a simple ion or if it's something more complex? And again, this is a rule that always works. I've said earlier, there aren't many sort of rules that always work. There's usually a but at A level, isn't there? This one doesn't have one. Anything that's 3 plus or less, because metals will all have positive generally oxidation numbers. Obviously the element's 0, and then they can go up to higher, so it'll be sort of 7, isn't it, for manganese and some others. So 3+ or less will be simple ions. So vanadium 3+ is vanadium 3+. Copper 2+ is copper 2+. Silver plus is silver plus. Anything 4+ or more will not be a simple ion. It will be covalently bonded, usually to oxygen. It'll be what we call an oxyanion. And I've put a few of the common ones there. There are obviously many other examples, but anything 4+ or more will not be a simple ion. It requires too much energy to remove 4 or 5 or 6 or 7 electrons. You know, a manganate ion, MnO4-, is not an Mn7+ ion with 4 O2- oxide ions stuck to it. It's a covalently bonded species. It does carry a negative charge. It is an ion overall, but it contains covalently bonded manganese. It's not Mn7+ ion. It is a nominally an oxidation state of 7+ if you follow the oxidation state rules. But that accepts that these rules work every time. 3+ or less simple ions, 4+ or more, never a simple ion. It's an oxyion. It's got usually oxygen bound to it. Things like manganate, dichromate, and some of the vanadium species are the obvious examples. There are others, of course. Okay, let's look at complexes, because that's one of the important points about transition metals. They can form complexes, and of course then you need to know some of the aqueous chemistry of some of the complexes. That will vary from board to board, so we're not going to look at all of that. So that's a complex. You know your definitions. You have to define any of these things. So a complex is a molecule or ion made up from 2 or more species that can exist independently. So the transition metal ion can exist on its own. The ligand, the thing that's going to join to the transition metal ion, can also exist as an independent entity on its own. So a ligand, of course, is anything that's got 1 or more lone pairs to coordinate with the metal ion. Now, of course, this is where inorganic chemists like to give something a different name to what organic chemists do for the same thing. Because in organic chemistry, I'm an organic chemist by training, my PhD is organic. Organic chemists wouldn't call something with a lone pair a ligand, we'd call it a nucleophile, but it's exactly the same thing. And of course, coordinate bond, as you all know from AS, is a covalent bond formed by one element having a lone pair, another element having an empty orbital. The lone pair is donated to the empty orbital, forming a shared pair of electrons. It's a different way to form a covalent bond, but in every other respect, it's identical to a covalent bond formed from 1 electron from each element. Completely indistinguishable. And coordination number, of course, is the number of coordinate bonds, number of pairs of electrons, the lone pairs that are being shared between the ligands and the metal ion. It's not the number of ligands necessarily, unless the ligands are all monodentate. It's the number of lone pairs. So watch out for that one, number of coordinate bonds, which is, of course, the number of lone pairs donated. And you often write them in this sort of formula. You put them in square brackets, which could potentially be confused with concentration if you're not careful, but if it's got square brackets and it's got a transition metal in with something else, it's probably a transition metal complex. There'll be 1 metal ion in usually. There'll be a number of ligands, usually between 1 and 6, and it may or may not have an overall charge. Complexes, notice I'm calling them complexes. I'm not calling them complex ions, because they aren't all ions. Some are neutral, some are positive ions, some are negative ions, but you can get neutral complexes as well. They aren't all charged overall, although they will contain a metal ion, and they may contain a negatively charged ligand as well. So shapes of complexes, often our students asking me, well, how do I remember? I'm trying to give you lots of little sort of rules and little ways to remember things here as part of this, try and make sense of it as looking at patterns and so on, because a lot of students tell me they can't see any patterns in transition metal chemistry, whereas actually there's lots. Basically, 99.999% of the complexes you've studied are octahedral. So if in doubt, it's octahedral. But of course, what they're going to ask you about in the exam, they might ask you about an octahedral one, but they'll probably ask you about the 2 or 3 that aren't octahedral. So just learn the 2 or 3 that aren't octahedral, everything else is. Tetrahedral. The only tetrahedral examples are the ones that you come across, the ones with chloride as a ligand, formed with concate Cl. So I think every spec has the cobalt one, some specs have the copper one as well, but they're the only ones that are tetrahedral now, as far as you're concerned. The only linear one is the one with silver and ammonia. As you know, that's the active species in Tollens reagent, ammoniacal silver nitrate. So dissolved silver nitrate in aqueous ammonia. That's what you'll get, AgNH3 twice. It's linear. And again, in some specs, there's only 1 square planar complex. So the 4 ligands are at 90 degrees like that. And that's cisplatin. It's not on every spec, but it's on quite a few of them. One of the world's first commercial anti-cancer drugs, of course, cisplatin. Transplatin doesn't work because it's the wrong shape. It's got the ligands in the wrong place. So if you learn that cisplatin square planar, the silver complex is linear, and the 2 with chloride are tetrahedral, everything else is octahedral. Sadly, I've never yet found a pattern with the colours. If anyone has found any sort of pattern with the colours, please let me know, because after 33 years teaching this and marking it, I've not spotted a pattern in the colours yet. Not to say there isn't one, but just I haven't spotted it. Let's look at some of the metal ion chemistry then. So in the notes I've given you, which you don't need to refer to now, this is just when if you come to look at this presentation later, because Mark is recording it, it'll go up on the part of the WMCC website. He'll send you a link, and if you view this recording later at your leisure when you're revising, and that's why I put these pages in, so you know which page of the PDF to look at for relevant information. So basically, the other thing that students would ask me is, how do I know if I'm going to see a soluble complex? In other words, I'm going to see a coloured solution, a transparent solution. Don't say clear at A level, please. It's transparent. And the general rule is, again, this has no exceptions. If they're an ion, if it's a complex ion, if it's got a charge overall, it's soluble. You don't need to know it's because it's solvated by water, but that's why. There's some simple examples. There are many others. If it's a neutral complex, it'll be a precipitate. The neutral complexes are insoluble. Charged complexes are soluble. And there's no exception to that rule, certainly for any that you study at A level. So there's another nice bit of sort of black and white, not shades of grey at all. Ions are soluble. Neutral complexes like hydroxides are all insoluble. You don't need to know why. So reactions, you need to know examples of each. Again, just depend on the spec, which of these you need to know. Acidity of metal 3+ versus metal 2+, that's AQA only. So we're not going to, well, actually, most of you are AQA, so I will mention this briefly. You need to know simple ligand exchange. You need to know ligand exchange with a change in coordination number. You need to know some more complex ligand exchange called the chelate effect. We're definitely going to look at that one. Whoops, sorry, forgot what's on this slide. So we'll briefly look. All these things have notes on in the PDF that you've got. They've all got examples of them. You know, make sure you know an example of each, because the exam can say, give an example of ligand exchange with changing coordination number. So you need to learn at least one of them. So acidity. This is for most of you, because most of you are AQA, so I'll just apologise to the few OCR students. You can have a little snooze for 30 seconds because this isn't on your spec any longer. Used to be. So the AQA students will know that the metal 3+ ions are acidic because metal 3+ is small and highly polarised. It's a very small ion with a high charge. It can distort the water molecules enough that a water can come in, or even a base can come in and deprotonate the water molecules that are the ligands on the ion. And so you get H3O+ release, and of course H3O+ in water is what makes things acidic. The 2+ does that to a much lesser extent. So the 2+ effectively are not acidic to any significant extent, because the 2+ ion for the same metal is obviously larger, it's got less charge on it, it's less polarizing. Oh, somebody's raised a hand, so if you want to ask a question, please, you post it in the chat. Oh, sorry, someone said they can't use the poll. It's not open at the moment because there aren't any questions on, but sorry, Matt, a few of you joined late. To join the polling, you need to type in ra.ombia.com and the code is PH10. If you scroll back in the chat, it's the first thing I put in the chat. But so, yeah, if you join later, you won't see the earlier chat, will you? So yeah, ra.ombia.com and PH10. But so there aren't any Ombia questions at the moment, so don't worry if you can't see one. Someone did raise a hand, but I can't see what that. You'll all be muted by Mark. So if you've got a question, hang on, keep the thought until the end, and I'll answer any questions at the end. Mark will look at the chat, and you can unmute and ask me questions at the end. So 3+ ions are acidic, Fe3+, Cr3+, that's not on the spec anymore, and so on. 2+ ions are not effectively acidic because it's a larger ion and it's got lesser charge. Again, there's full notes explaining this and giving these equations and so on in your booklet that you've got. It's gone on the chat, I can't. There we go. So there's various equations like that. You can lose the first 2 protons just with water. Water is not a strong enough base to deprotonate the third one and actually form the precipitate of the hydroxide at the bottom there. You need to add a stronger base, such as ammonia. I know ammonia is a weak base, but it's a stronger base than water. You need ammonia or OH- or even carbonate to produce the precipitate of the hydroxide. You won't get that third equation working with water. Water is not a strong enough base. So as I said, dropwise OH minus. These are all summarised in your summary table in the booklet for each exam board, because you each need to know different reactions. So OH minus is a strong base. Dropwise, it acts as a base. You get the hydroxide. Excess still acts as a base. You still get the hydroxide. Some dissolve in excess, some don't. You need to remember the ones that dissolve. Again, there isn't particularly a pattern. Ammonia is a weaker base. So dropwise, it acts as a base. You get the hydroxide precipitate. Excess, ammonia acts as a ligand, and you get ligand substitution, and the hydroxide precipitate usually dissolves, and you get sort of metal ammonia 6, sort of soluble complex ion. With carbonate, very weak base. The properties are governed by the acidity of the metal 2+, the metal ion. Metal 2+, you'll get a precipitate of metal carbonate, including copper. Copper is the only 2+1 that's just about acidic solution, but you'll get copper carbonate. You won't get effervescence of the copper hydroxide. 3+ ions, much more acidic, so they react with the carbonate as an acid, and you'll get the metal hydroxide precipitate. You get effervescence of CO2 because the metal 3+ is strong enough, it's strongly enough acidic to react with carbonate. Metal 2+ is not strongly acidic enough to react with carbonate, even copper. So simple ligand exchange, there's an obvious one. Copper H2O6 with hydroxide going to copper OH2 H2O4. That's octahedral solution to an octahedral blue precipitate, and that doesn't dissolve in excess. It will stay as a precipitate of the hydroxide. There's loads of other examples. I'm going to show you some ligand exchange now, but not involving that, involving nickel salts. Now don't worry, nickel's not on the syllabus, but that doesn't matter. What we've got in here is some nickel H2O6. So most transition metal complexes in water are the metal H2O6. And you can see that one's green. And what we're going to do is I'm going to actually add a bidentate ligand to it. I'm going to add ethylene diamine, or 1,2-diaminoethane, as you would have to call it in the exam. And so let's watch me do that in the second beaker. I'm leaving the first one as control. So I'm adding 1 mole of ethylene diamine. So I'll keep calling it ethylene diamine, sorry, EN for short, 1,2-diaminoethane. And you can see that the complex goes blue. So what we've done is replaced 2 of the waters with a bidentate ligand, a ligand with 2 lone pairs. There's 2 lone pairs on the 2 nitrogens, and we get that complex there. And you can clearly see the color change is blue. This is really an unusual reaction, this, because we're going to stepwise replace the ligands 2 at a time and get a different colored complex every time. That doesn't usually happen. So let's now replace 2 more waters. I'm adding now effectively 2 moles of diamine to 1 mole of the complex. And you can see there, that's a lovely indigo color. Not purple, it's indigo. Might spot a pattern here. I do this as part of a demonstration lecture called Colourful Chemistry. It was a demonstration given to me by one of my now long retired colleagues here at Newcastle. He used to do a lot of schools lectures and stuff for our Salters Festival and so on. Green, blue, indigo. There's a bit of a pattern there, isn't there? So I do this as part of my Colourful Chemistry lecture. And I'm sure a lot of you are thinking, green, blue, indigo, the last one's going to go violet. So let's see if it does. Because occasionally, of course, we can get an anomalous result or something that doesn't follow the pattern. Fortunately, this isn't one of them. And this is a really unusual reaction. So it's not one that's on your specs now. Nickel chemistry isn't on anybody's spec any longer. It used to be on EdXL until a few years ago. I don't think I've ever taught it. I don't think it was even on AQ. I must have done a bit of it on AQA when I first started teaching, but it's called J&B then. But that's a lovely stepwise replacement of ligand, and you get a different coloured complex each time. And at some point, and it might be now or it might be slightly later, we're going to have a look at this indigo and this violet complex, because you may or may not know that they, or you should know for your specs, that they each have a type of isomerism, stereoisomerism. It might be on the next slide, it might be a little bit later. I can't quite remember because I haven't done this lecture since last year. Yeah, it's mentioning it here. So the di complex can show cis-trans isomerism, and the tri one actually shows optical isomerism. You get optical isomerism with transition metal complexes as well. And it's going to show you it now. Brilliant. So these are some X-ray crystal structures of the 2 complexes. I'll mention a resource at the end of the lecture where you can go and look at these 3D structures yourself. So there's the 2 di bidentate ligand complexes, and it does it with if you've got complexes that have 2 bidentate ligands and 2 monodentate ligands. So the one on the left is the cis isomer, where the 2 bidentate groups are close to each other. The trans isomer is an easy one to visualize. That's where the 2 bidentate groups are opposite each other, and the 2 remain. Usually happens with octahedral complexes, and the 2 remaining waters are just up and down. So I'm showing you the nickel one here, but it works for lots of other elements, transition metals as well. And the 3 one actually has optical isomers. They are mirror images. So you can see there that there's 2 different forms of the nickel EN3 or any bidentate. So it work with oxalate. Sorry, I've forgotten the ethane dioate is the proper name for it. I call it oxalate because I've been doing these things for a long time. You'd have to call it ethane dioate ligand. That's also bidentate. And 3 of them around a metal center, when it's octahedral, you will get this effect here where you've got the mirror plane down the middle there. You've got 2 optical isomers. So watch out for that. They will sometimes throw that at you. Hopefully you hope they don't get you to draw them because they're a little bit complex, more complex than drawing an optical isomer in organic chemistry, which is usually a bit more straightforward. Okay, and just to briefly mention 2 important biological complexes, of course, that make use of this. Found in the red blood cells of all animals, of course, allow oxygen transport. Hemoglobin. So yes, it's an iron complex, and that's why, of course, blood is red. It's got an iron 3. It's not an iron atom, it's an iron 3 ion. And of course, rust is also iron 3 oxide. So that's why rust and blood are a similar color. And the other one, of course, is a green substance found in the leaves of plants, catalyst of photosynthesis, chlorophyll. Now, chlorophyll, notice, doesn't have a transition metal ion in it. It's got a magnesium ion. It's not green because of the magnesium ion, because magnesium is not a transition metal. Magnesium compounds are not colored. It's other effects in the molecule that cause chlorophyll to be green. It's not the magnesium complex. But there's 2 completely different complexes found in completely different organisms. One's found in plants, one found in animals. Do completely different jobs. But structurally, they're quite similar, aren't they, if you sort of glance from one to the 2. So I'd like to thank my colleague Andy Brunning, who runs the Compound Interest website, for kindly providing these images for me. So if you haven't found compound chemistry or compound interest, go and have a look at the website. It's got hundreds of infographics covering all sorts of topics across chemistry. I know a lot of teachers print them off and put them up on your chemistry notice board. And he's also actually the chemistry subject officer for OCR. Now that's his day job, but he did used to be a chemistry teacher, and so he does these infographics in his spare time, and they really are excellent. So I'd certainly recommend them. And this is the resource I was mentioning that we can go and look at the online 3D structures of those complexes and so on. It doesn't just cover transition metals. There's a whole list of topics you can see there. EZ and optical isomerism in organic molecules, VSEPR, and so on. The link's there. You'll be able to have a look at the link when you look at a recording of the lecture afterwards. And there's a whole range of things where you get to look at real 3D crystal structures, research structures. It's a worldwide research database called the Cambridge Structural Database. And you get to answer questions looking at real crystal structures. So that one on the screen there at the moment, that's actually the structure of aspirin. I'm sure a lot of you have made that as one of your required practicals this year. Okay, so ligand exchange with changing coordination number, various examples. The obvious one is where you're going from water, aqua, to chloride, because it changes from coordination number 6 to coordination number 4. Reason being, of course, is because a chloride ion is much bigger than a water molecule, and so you can't fit 6 chloride ions round copper or round cobalt, because those ions are getting quite small on the right-hand side of the periodic table. Copper 2 plus, cobalt 2 plus are quite small. You can fit 6 waters around them. You can't fit 6 chlorides around, because chloride is a much bigger ion than water is a molecule. So that's why it changes coordination number. You can only fit 4 of them round. And finally, to mention something called the chelate effect. Again, when I did this live in Birmingham a few years ago, I actually did a demonstration of this, but unfortunately, I didn't have the chemicals handy or be able to get into a lab to video it, although I would have shown you this happening live. But the chelate effect is where you replace a unidentate ligand, usually, with a multidentate one, and you get a massive increase in entropy because you're taking 6 ligands off, but only putting 1 on. So there's a big increase in sort of number of moles on the right-hand side of the equation. And the classic example of this is to use EDTA, ethylene diamine tetraacetic acid. That's not a UPAC name, but we call it EDTA. You call it EDTA. And overall, if you react EDTA with copper hexaaqua ion, you can see you've got 2 moles of stuff on the left. And on the right, you've formed your copper EDTA complex. EDTA is a hexadentate ligand. It's got 6 lone pairs. It replaces all 6 waters. We've got 7 moles on the right. Oh, that must be going to come back to that. Apologies. Thought there was something else underneath. So there's your copper H2O6. You're breaking 6 copper oxygen bonds to take those 6 waters off. To put EDTA on, you're forming 4 copper oxygen bonds, so they'll have exactly the same energy. And the 2 copper nitrogen bonds, or copper nitrogen and copper oxygen, have a fairly similar sort of bond dissociation enthalpy. So overall, the delta H for that process is very, very close to 0. There's very little enthalpy change for that at all. You're breaking 6 CO, forming, sorry, 6 CuO, you're forming 4 CuO and 2 CuN. So overall, delta H very, very close to 0. But because you've got a massive increase in the number of moles on the right, you've got +5, start 2 to 7, you've got a massive increase in entropy. That's the equation you're very familiar with, of course, for entropy change and Gibbs free energy. If so, delta H is effectively 0, so it can disappear out of that equation. Delta S is extremely large and positive. There's a big increase in entropy. So delta G is extremely large and negative. So it's very, very favorable process, very, very feasible process. And the product is very stable. It will not undergo further substitution. You've got no chance. If you have that solution, and if I had the time to make the videos, I'd have shown you this live. I'd have made that copper EDTA complex, which again is a solution because it's charged. And then I would tip in loads of sodium hydroxide solution, and it would still remain that blue solution. You don't get the precipitate of copper hydroxide. You would not get a precipitate of copper hydroxide. There's no way a monodentate ligand hydroxide is going to displace a hexadentate ligand EDTA because of this chelate effect. There's a massive entropy drive to form it. There's a massive disincentive in entropy in that bottom equation to unform it. You're having to go from 7 moles on the right to 2 moles. That's a massive decrease in entropy. That's just not going to happen. It'd be a big positive delta G. And so that does not happen. So it forms an EDTA complex. And some of you may know it's actually quantitative. Any transition metal ion with EDTA reacts quantitatively, and you can actually use that as a measure. You can do titrations with it and estimate the amount, calculate precisely, in fact, not estimate, the amount of a transition metal ion in solution by doing an EDTA, what we call a complexometric titration. So there are patterns to learning the reactions. You've got a summary sheet, say, for each of your different exam boards in the PDF. So look at the relevant one for you. There's a summary table of the aqueous ion reactions you have to know about. And then on the back, there's my sort of rules for your spec, how sort of 4 or 5 things you have to learn to remember it. You don't have to learn all the things in the sort of 25 boxes or however many there are on the table. So for example, everything with dropwise NaOH gives a precipitate the hydroxide. So there's 5 or 6 reactions boiled down to 1. All NaOH give a precipitate the hydroxide. All dropwise ammonia give a precipitate the hydroxide. So there's potentially 12 reactions boiled down to 1. Excess conc HCl all gives MCl4 2-, the 2 tetrahedral complexes, and there's various others as well. So, and I've got those rules for you there in the booklet. What I used to do with my students is give them the blank table. They used to fill in all the shapes, formulas, and colours of the complexes, and then I used to get them to go through and come up with the rules themselves. What are the patterns? And there are patterns in the way these behave, apart from, as I said earlier, the colours. Okay, let's now move on to a little bit of redox chemistry. We're not going to look at oxidation numbers and so on. That's a bit basic. We're going to look at sort of calculations with redox. So you need to fire up your calculator for the next few minutes. So there's some example calculations on page 26 and 27. If you can see the PDF, don't worry if you can't, because I'm going to show you some calculations here. They're basically exactly the same as acid base, except instead of being 1-to-1, 2-to-1, or 3-to-1, you've got weirder stoichiometry, weirder number of moles that react together. There is a transition metal reaction. I can't work out which one it is, but it's one I used to give to my students a long time ago. And when you write the balanced overall equation, it's 3 to 7. And I can't remember which one it is, but I'm not giving you that one today, don't worry. So usually the way to work out a calculation involving moles is 3 steps. There's different ways of doing it. More than one way to skin a cat. I say that as someone who likes cats. We've got 3. But more than one way to skin a cat means there's more than one way to do something. And calculations is a classic example of that. There's more than one method that will give you the right answer. And wearing my examiner's hat, as long as you get the right answer, you must have used a valid method. It will always score the marks. We're not going to go, oh, well, you got the right answer, but you didn't use the method in the mark scheme. So ha ha, we're giving you no marks. That's silly. You know a different way of doing it. Absolutely fine. The way I do it, the sort of standard way, but there are others. If you do it a different way to this, don't worry. You're very late on in year 13 now. Don't change. Stick to what you know and what you're used to. But this is I think this is the way I used to teach it. This is the way a lot of people teach it, but I appreciate not everybody. 3 steps. Work out the ones of the moles you know. That usually uses a titer. Step 2, use the equation, which you're always supplied with, to work out the moles of the other one it's reacting with. And then step 3, turn that into the required answer. That step 3 can sometimes just be 1 step, or step 3 might involve 2 or 3 steps, depending on what you're actually doing. Okay, so here's an example one. I think this is one of the ones that's in the notes. So 25 cubic centimeters of C2O4, that's ethane diorate, reacted with 22.7 of 0.02 manganate. Calculate the ethane diorate concentration. So there's the moles of the known. I use CV over 1,000. I always put the 1,000 in because it reminds me that the volume is in centimeters cubed, but the concentration is in decimeter cubed. You don't have to have the 1,000 there. If you just remember it's N equals CV, but remember to turn your volume into liters, or you get a stupid answer. So there's the moles of manganate. There's the balanced equation. So it's 2 moles of manganate to 5 moles of ethane diorate. So I need to multiply it by 5 over 2. The ethane diorate's bigger than the manganate. 1.14 times 10 to the minus 3. Let's convert that into the required answer. It's C, concentration, 1,000 N over V. Substitute the numbers in. Again, the 1,000's there because I like to have it in because that's automatically doing the centimetre cube convert to litres conversion for me. And the answer is 0.454 molar. Moles per decimetre cubed. I'm old-fashioned. I put capital M, molar. It's quite correct. It's an alternative to mole per decimetre cube. You've probably got to write mole per decimetre cube to keep the exam board happy. But capital M, which you'll see in all my notes and all my slides, is the same thing. It's molar. It means 1 mole per decimetre cube. Notice answer given to 3 significant figures, because as you know, that's the default accuracy of your final answer, unless, of course, RTFQ. Read the full question. I haven't got that. I normally have that animated at the start of this presentation. I haven't done that. Read the full question, RTFQ. If it tells you to give it to a different number of sig figs or decimal places, then do that. Otherwise, default is 3. So, here's one for you. So this is an OMBIA question, and this is different. OMBIA is quite powerful. It's much better than the Zappers. The Zappers, you can only have multiple choice questions. Here, I want you to type the number that you come up with as the answer to the appropriate number of significant figures. And the computer at the end will give me the 5 most common responses. Again, on that previous question, notice I gave the answer as a decimal, and that's purely because that's easier for me to type into a PowerPoint, because I'm not going to faff about doing superscripts to do standard form. A lot of students ask me that, can I leave my answer as a decimal? Can I convert it to standard form? Again, RTFQ. If the question does not specify that the answer must be in a particular form, you can give it in either. You can leave it in standard form, you can give it as a decimal. However your calculator throws it out. Basically, the important thing is, have you got the correct answer, and is it to the correct number of significant figures? Either standard form or decimal. I've never yet seen, certainly on an AQA exam, them asking you to give an answer as a decimal or to give it standard form. Not to say it won't happen in the future, because they expect to be able to work with obviously both systems, but normally either is perfectly acceptable. You do get some mathematicians asking me, can I leave it as an improper fraction? Because clearly in maths, A-level calculations or whatever, you're allowed to leave things as improper fractions. I don't think we would accept that in a chemistry exam. I want to see a decimal or standard form, which effectively is decimal as well. So no, I don't think we'd accept a fraction as the final answer. So I usually have 2 of these calculations, but I'm noticing the time, and we want to have a quick look at catalysis at the end. So what I will do when we've had a look at the answer to this question is I will show the slide for the next question and just leave it up for a few seconds. And then I'll put the slide up with the answers on, so then the recording will pick it up and you'll be able to come back and have a look at the recording and have a go at the second calculation yourself at your leisure, because obviously you just stop the recording when the question slide is up, have a go at it, and then just move on a few seconds and you'll see the answer. So I'll show you the next question and answer, but I won't get to do it. So I'm conscious that it's 8 minutes to 8, and I don't want to overrun much if at all. We've all got other things to do, I'm sure. At least most of us haven't got to travel anywhere. I've got to travel 15 miles home back to Durham, but most of you, I'm sure, are in the comfort of your home, so you won't be going anywhere. So I'm not going to overrun though, hopefully, not by much. And I want to show you a couple of examples of the two different types of catalysis at the end of this lecture. That will take about 5 minutes. Okay, so we've got about 90 of you with the answer. That's good. These things always take a little bit longer. I shall stop polling now, and let's see what's this will display the 5 most common answers that have been typed into Ombia. So, oh, very good. See, some people have put units in. The problem is, yeah, Ombia annoyingly turns it all into capitals, so don't worry about that, but we know that's really lowercase. So the 2 most popular answers seem to be 0.0353 and 0.035. Oh no, 1, 2, sorry, 6. I can't. Oh, 6 is other. Sorry, I can't see other. Okay. Some of the others are just variants, because obviously 0.353 molar, and notice it, if you leave a space and don't leave a space, it picks it as 2 different answers. But most of you have clearly got 0.353. And oh, of course, I can't tell you what the correct answer is. This is a working out. Sorry, the correct answer is 0.0353. Well done. A couple of you, or a few of you, put 0.35. That wouldn't get the last mark, because that's only to 2 significant figures. It must be to 3 significant figures unless the question asks you different. So the few of you that put 0.35 wouldn't score the last mark. You get the rest of the calculation marks, but you'd lose your final answer mark because it wasn't to 3 significant figures minimum. So I'll say we haven't got time to do this, but here's the next question. I'm just going to leave it on the screen for 10 seconds. So it will be picked up by the recording. When you watch the recording at your leisure at some point in the future, you can pause this, have a go at the question, and then here is the answer. So I'll just leave this on for a few seconds. So again, you'll be able to pause the recording, do the calculation, and then pause it a few seconds later and look at the worked answer here. This one's a bit more involved. This, I think, is like a 5 or 6 mark question, because you notice step 3 has a couple of marks to it to work out a percentage purity or percentage of iron in the sample. Okay, so I'll let you have a go at that at your leisure, if you wish. And there are, I think, 2 or 3 titration examples in your booklet as well. So again, you can get the appropriate page, just cover over the answer, work it out yourself, and then you've got the worked answers there for you. I think there's 3 worked examples of a redox titration in your PDF as well. So we're going to finish up the last couple of minutes just having a quick look at catalysis. It means I can show you a couple of nice demonstrations. So you may or may not know, hopefully you've all done this by now, or it's one of the last topics I used to teach at AS chemistry, to A2 chemistry, sorry, transition metals. You will know there are 2 types of catalysis. There's homogeneous, where most things are in the same phase or state, and there's heterogeneous, where they're in different phases or state. And of course, transition metals are good at both, because transition metals are also good at transferring electrons. They've got multiple oxidation states. They're very good at gaining and losing electrons. So a catalyst, of course, is a species which increases the rate of chemical reaction by providing an alternative reaction pathway with a lower activation energy, and it's recovered unchanged at the end of the reaction. So they're the 2 things you need to put down to score 2 marks in an exam for what's the definition of a catalyst. Lowers the activation energy, alternative reaction pathway, and recovered unchanged at the end. But you can't normally see catalysts working. I'm going to show you at least one catalyst working in the next couple of minutes. So homogeneous catalysis is in the same phase or state of reaction, usually in aqueous solution. We're talking about here. Obviously, solids don't react very well with solids, and gases can react with gases, but most gases react with each other, often don't need a catalyst. We'll talk about that later though. But homogeneous ones are often in solution. The catalyst take part in the reaction. It usually changes oxidation state, but it changes back again. Hence why transition metals are good at it. On the downsides of homogeneous catalysis is you need equimolar or greater quantities of catalyst. You need a large amount of catalyst in solution. That's the downside if your catalyst is expensive. And on a couple of examples, the AQM, there's a couple of examples of homogeneous catalyst you need to know. I'm not going to go through that now. All the equations and the information are in your book, your PDF booklet that that Mark you. I'll send a link to it before the lecture. So I'm going to show you a homogeneous catalyst actually working. This is brilliant. I show this to all my students when I taught GCSE at A-level. It's the only example I know of a catalyst actually working. So what I'm putting in this flask is some potassium sodium tartrate. Not particularly important, but it will decompose, give off carbon dioxide gas. I'm going to dissolve it up in some hot water from a freshly boiled kettle. So we've got a bit more energy in hot water, of course. That will help the reaction to proceed. And we're also, of course, dissolving the solid because solids don't tend to react very well. The particles can't move. So I've got to react it with something. I'm going to react it with something nasty. I'm going to react it with 100 volume hydrogen peroxide. So when these two react together, it'll produce oxygen gas and carbon dioxide gas, and we should see lots of effervescence. Number of year 13s who write fizz in A-level exams. And annoyingly, I have to give you the mark because you can't be bothered to spell effervescence. It's effervescence. Can you see any effervescence in this? It's a rhetorical question. No, you haven't got your mics on. No, you can't. The reaction's too slow. We need to speed it up with our catalyst. And here's our catalyst. Cobalt chloride solution. Transition metal, cobalt chloride. I'm going to tip it in and run away. And you'll now see why I've got it sitting in that big blue tray. You'll go, oh, not much is happening. See, everyone happens these days, modern society, everyone expects things to happen instantly. Now, it does get going eventually. It's got to overcome the activation energy. It can take a little bit of time. I think it has overcome the activation energy now. You can see the reaction is a bit more vigorous. Notice it's green in the middle because it turned to a different oxidation state of cobalt. But if you watch the solution in the flask now as the reaction subsides, you'll notice it's reverted back to its original pink colour. I'll come and pick it up and stupidly hold it against my dark coloured lab coat so you can't really see that. You can sort of see against the back of the lecture theatre, which is white. It has turned back pink. So it certainly does take part in the reaction. I get annoyed when I used to walk through classrooms with non-chemists teaching catalysis. A catalyst speeds up a reaction but doesn't take part in it. Of course it does. It lowers the activation energy, but you get it back at the end. There's the chemistry. The cobalt turned to cobalt-3, gave an electron to the reaction. This is redox reaction. But at the end of the reaction, the cobalt-3 gets its electron back, reverts back to cobalt-2. So overall, the catalyst is unused. There was a gram of catalyst in that. So I don't want the solution made up, but I make it up using a gram of catalyst in a pot. I normally make the solution up fresh in front of everybody. And if you evaporated all those solutions off, you'd get the 1 gram of catalyst back. None of it's been used up. And finally, then heterogeneous catalysis. Heterogeneous catalysis, don't know what I'm there, sorry. These are in different phases and states. This is often where the catalyst is a solid surface and the reactants are gaseous or sometimes liquid. It's going to be liquid, the one I'm going to show you in a moment. Catalyst provides a surface, active sites for the reaction to take place. So, of course, again, transition metal is very good at that, either the elements or it could be, of course, their compounds. It doesn't have to be the metal. Surface area, of course, is an important factor, as you know. So you have to balance things like surface area versus cost. So expensive catalysts like silver and so on are often sprayed onto inert material, which has got a large area. So you're only having a very thin layer of silver because only the surface can react. But by spraying it over something that's got a large surface area, you're maximizing the surface area of the silver or other valuable transition metals, platinum and so on, but only using a small amount of it. And of course, you can also be aware of catalyst poisoning, that impurities in your start materials can get into the active sites, block them, and therefore inhibit the catalyst. It becomes less and less effective. So most industrial plants, about once every 4 years, we stop it, take the catalyst out, give it a clean, put it back in again, and off they go again. So know at least one example, including the relevant equations. I'm going to show you one now. So the final thing I'm going to show you is, it is an example of heterogeneous catalysis. A lot of people don't realize it. I'm going to show you the ubiquitous elephant's toothpaste demonstration, but my version of it. So you've got large measuring cylinder there in my same blue tray. This wasn't filmed at the same time. And I'm going to use Fairy liquid because Fairy soap was invented in Newcastle. It's a Newcastle product, as is Andrews liver salts, as is Domestos bleach, and Lucasade was also invented in Newcastle. Sadly, none of these things are made in Newcastle anymore, but they were all invented there. So I've put some detergent at the bottom of this tube, and the catalyst is powdered manganese dioxide, MnO2. It's manganese 4, but it's the dioxide. It's a compound of manganese. It's going to provide the surface area. It's a powder, so we get a large surface area, should make the reaction very fast, giving it a good shake. I don't know about you, but I like stripy toothpaste. So I'm going to give my elephant some stripy toothpaste. I'm going to give it some red stripes and some green stripes. Would you believe I have to make my own food colouring now? That's why it's got hazard labels on, because you can't buy this nice thick gloopy stuff now. It's presumably been banned because of all the E numbers. So I have to make my own. And again, we're going to use peroxide for this, because peroxide with this catalyst will break down to water and oxygen. And the oxygen will bubble up through the detergent and make lots of lovely stripy toothpaste, but it's a heterogeneous catalyst. The MnO2 will rapidly catalyze the decomposition of the peroxide. It's the same 100 volume stuff. There we are. So same blue tray. This wasn't filmed on the same day or even the same week. This is I don't do this as part of Colourful Chemistry. This is part of a primary school lecture I do called Chemistry in Your Shopping Basket, where there's 4 items in the shopping basket connected by crude oil. And so I use the detergent, which of course is made from crude oil. And there's some lovely stripy toothpaste. We've accelerated the decomposition of the peroxide from our point of view using a small amount of that MnO2 catalyst. But again, if you collected all the foam, you could get the MnO2 catalyst back out. I don't bother, there's only a small amount of it. I'll wash it down the sink. Hopefully no one from Cleats is listening. And there we go. So there's some nice stripy toothpaste. We've catalyzed the decomposition of peroxide to water and oxygen using MnO2, which is powdered, got a very high surface area, very rapid increase in reaction, lots and lots of active sites. So there we are. That's brought me to the end of the lecture. Just a brief mention. Again, I'll just put these up. You can look at these at your leisure at the end. There's some other resources. If you're also doing A-level biology and AQA or Salters or EdXL chemistry, you've got some biochemistry in your A-levels. And if you're doing A-level biology as well, obviously you've got lots of stuff about proteins and so on. This is a resource for the European Protein Data Bank. And those of you also doing A-level biology, only this is a resource for the AS lipids content done by my Nuffield students remotely last summer, and they did a really good job. So there's 3 different resources I've mentioned to you today. You can come back and look at the links when you look at the video recording that will help you in the sort of towards your revision in your last couple of months of A-level chemistry. So I'd just like to thank WMCTC again for inviting me to give my annual revision lecture, and to Mark for hosting, and to all you guys for turning up and taking part. I hope you've all found it useful. And I've overrun by a few minutes, but I'm not going anywhere. If anyone does wish to hang around and ask some questions, I'm quite happy to stay here and attempt to answer them. And obviously,
thank you.
Good luck with the A-levels in the summer. And if you are applying to university, which I'm sure most of you are, I hope you all end up where you want to be.
Excellent. Thank you very much, Peter. Thanks for those kind words at the end. And thank you very much for the most excellent revision lecture as well. And although we couldn't see them in person, those demonstrations worked really well. The videos were excellent. So great way to see them. Yeah, brilliant. And I think we started a bit later, so I don't think you overran. I think the timing was perfect. So well done on that front. Excellent. So as you mentioned before, if people do have questions that they'd like to put to Peter, please type them in the chat. I've got a few come up here. Someone was mentioning, why is it that in transition metals, in order for it to be optically active, it doesn't need a chiral center? If so, when rotating through plane polarized light, how would you distinguish between the L and D enantiomers?
Right, well, the answer is it does have a chiral center, but it isn't an organic chiral center. So organic chiral centers, of course, are a tetrahedral carbon atom, usually. It can be other elements as well, but for A-level, you're restricted to carbon. And of course, in organic chemistry, a chiral center is a 4-coordinate carbon in a tetrahedral arrangement, and that's what gives rise to 2 mirror images, because you've got 4 different groups on. That slide I showed you earlier, if I can try and find it back again. Why can I not escape? Oh, it's because I looked at the chat, my fault. If I get the slide back, it does have a chiral center, but because it's a transition metal, the chiral center is actually octahedral. It's 6 coordinate because it's a transition metal. So there we are, there's the slide. So you can, if you study those 2 structures, you can see they are clearly mirror images. If there's a mirror plane down the center there where I've put the cursor, one of those is a reflection of the other. So they are a pair of enantiomers. They are optically active, and you detect them in the same way. One will rotate plane polarized light in one direction, or solution of one will rotate plane polarized light in one direction, and a solution of the other will rotate plane polarized light in the opposite direction, the same angle. The only difference is they are chiral. You can see the mirror images. They're not superimposable. If you rotate that right-hand structure round so it's facing the same way and try and put it on top of the left-hand one, the left-hand one's got the bottom bidentate ligand facing towards you. The right-hand one, if you rotate it round and superimpose it, has got the bottom bidentate ligand pointing away from you into the board. They are not superimposable. It is a chiral center. It's a transition metal chiral center, so it's octahedral. I'm sure there are tetrahedral things that do it if you put four different ligands on, but that's, imagine, quite tricky to do. But yeah, it is chiral. There are two mirror images, and you detect them in the same way. Their effect on plane polarized light.
Excellent. Thank you for that. Although we didn't get to the electrochemistry, someone's obviously read up on the spreadsheet, which is great on your handout. And quick question: the related exams, in terms of the redox equations, do students have to know these, or are they provided?
No, well, I know there's one equation that AQA expects students to know, and that's the half equation for manganate MnO4 going to Mn2+, because it's so common. But then I would say you don't need to learn it because you know the rules for working out half equations, because in an exam they can ask you to construct two half equations if they give you the reactant and product. And once you've got the two half equations, you can put them together to get the full equation. So I would argue you don't need to learn any of the redox equations, because the ones they want you to do, they will give you in the exam. Specifically for electrode potentials, no, nobody is expecting you to learn the redox half equations and the electrode potential values. They will give you a table that contains any of that data that they want you to use. They might ask you, say, to put them together and construct full equations from half equations. They may give you a reactant and product and say, construct a half equation. That's quite a valid question. But no one's expecting you to learn any redox equations, and they're certainly not expecting you to remember any electrode potential values. I don't think I can remember many of them, to be honest, apart from one or two of the obvious ones. The hydrogen electrode's quite easy to remember.
I must say, if anyone hasn't read the leaflet yet, that final section on electrochemistry, and especially the kind of, I thought it was a really clear and nice, succinct summary of the rules involved in selecting which is the left-hand and right-hand electrode, how to calculate the voltage of the cell. It's a really nice summary. So I certainly urge you to all to have a look at that. And I like the alternative method as well, where you sort of kind of almost plot the electric potentials on that line.
I found that really useful. I only found that out after I stopped teaching. If I was still teaching, I would definitely use that. That was given to me by one of the senior examiners from AQA, and I think that's brilliant, because if you plot it like that and it's in the booklet, as you say, Mark, you're bound to get it right. That is the right-hand one. It's more positive. That's the left-hand one. It's more negative. You can't possibly go wrong. And that's the thing that gets most students with electrochemistry is just the definitions. Which one's the anode, which one's the cathode, which is the positive one, which one does oxidation happen at, which one does reduction happen at. If you get the rules right, it's straightforward, but can you remember the rules? That's the crucial point. Exactly.
And also when you multiply up to balance the amount of electrons, not multiplying up the voltage at the same time, and just simple things like that.
Yeah, that often confuses students who go, well, surely if I triple this equation, I need to triple the electrode potential as well. But for whatever reason, the electrode potential is independent of the number of electrons transferred. It doesn't change if you use 3 times the amount of it. But as you say, you'll get, sometimes a student will triple the electrode potential. And then, of course, you'll get wildly the wrong answer for the E cell. And you'll predict often it doesn't work when it does, when it goes the wrong way. Yeah, absolutely.
And also, it's great that you echo the definitions as well and understand the conditions, because I think there have been questions where you've had a cell, and for example, the concentration of the electrolyte hasn't been standard concentration, and so by knowing the definition, you can then work out why it's not giving the voltage as expected. So.
Absolutely, yes. Yeah. I'll remember all this for next year.
Absolutely. So now I must admit, I checked your PDF initially just to check that it transferred okay, and I must admit I found it so interesting. I kind of read through it. So brilliant publication there.
As I say, Mark, as I said it to you earlier, that's a small fraction of a larger one that's sort of 98 sides long, which covers the whole of A2 chemistry that I use in my revision workshops. So yeah, there's lots more to come. And all I do for my Birmingham lecture every year, for my WMCTC lecture, is just give the students an abstract of just the topic we're covering. So I've done asses and paces in the past. I've done this before. We've done proteins and biomolecules and stuff. Yeah. So.
Yeah, excellent. And I must say, hopefully we look forward to welcoming you back to Birmingham, the Hanslet Theatre. And when students do arrive, I remember you kind of wheel in this great big stack of periodic tables and handouts, and it's great resources.
Hopefully next year we're back to normal. Yes, yeah.
Absolutely.
It's sadly just above the Birmingham universities. We're back to normal here at Newcastle. We've had students on campus and run school visits since last September. We've had a load on this last week because it's British Science Week.
Yeah, of course. Yeah.
Any more questions? Still quite a few people hanging about, so I don't know if anyone else wants to ask anything.
There is one.
We're all wintering on here nicely.
There is one popped up I've just noticed relating to catalysis, and someone's asking, do you know what factors affect the absorption strength? So, for example, why is it that platinum's a better catalyst than tungsten, for example?
Good grief, that sounds like an undergraduate question rather than an A-level one.
Doesn't it?
The answer is it's quite complicated. There's all sorts of factors that would affect I know there's one particular reaction that we used to do at AQA. It's gone off the spec now, but we used to do epoxidation of ethene to make epoxy ethene, because of course it's a good raw material for whatever. And of course you don't want that reaction to run away, because the epoxidation of ethene to make epoxy ethane is highly exothermic. And so that's why you use a silver catalyst, because actually it's not a brilliant catalyst. And so it stops the reaction running away. If you did it with palladium or platinum or something much better, you'd end up sort of blowing up your epoxy ethane plant every time you did it. So that's an interesting example. It used to be on the spec. It isn't on the spec anymore. They don't do epoxy ethane chemistry anymore, because of course it's a nice raw material for making lots of things like ethane diol and whatever. But they used to have to know that they use a silver catalyst, because silver's not the best transition metal catalyst, and you didn't want the reaction to run away and become too exothermic. So you actually used a relatively poor catalyst. And there are I'm sure there's other examples where that's done as well.
Yeah, excellent. Thanks for that. A couple of other questions snuck in while you're answering that. So one here. When hydroxide ion is used as a reactant to hydrolyze the hexa-aqua ions, does it happen because the oxygen in the OH group is more electronegative than the oxygen connected to the central positive ion, allowing for protonation of the OH?
Ooh, that's an interesting one. I'm going to switch to if I can do this now, I'm going to switch to my visualizer, because then I can scribble something. If this is going to work. Yay, okay. So, OH minus, I think you can all see that. Yeah, super.
You might have to stop screen sharing to make that.
Can you not see it, Mark, because I'm screen sharing?
I can see it, but it's small. But if you...
All right, is that any better?
I can see it. I don't know if... Can the others?
I'll start on another bit of paper and write a bit bigger. So you've obviously got I'll try and simplify these things here. You've got your water bonded to your transition metal. Let's just show one for simplicity. And of course, they're only acidic if this is metal 3+. There's metal 3+, very small ion, very high charge. It's highly polarizing. And so what it does is distorts the electrons, attracts the electrons in that bond and in those bonds. It weakens these OH bonds. And so, in fact, even just water can come in and do it. Water's a strong enough base to come in and remove H+ off those water molecules. So when we write the equation, it looks like it's a ligand exchange, doesn't it? It looks like the water is being replaced by OH minus in the equation overall, because you end up with a hydroxide complex. But in fact, that's not how it's doing it. It's the water or the hydroxide deprotonating the water molecules, the ligands attached to the metal. I'm not sure if electronegativity has got anything to do with it. I always explain it. It's the high polarity of the polarizing ability of the metal 3+ ion, because only really metal 3+ does it. Copper 2+ actually does do it to a little extent as well. Copper 2+ solutions are slightly acidic, but it's the metal 3+ because it's very small, very highly charged. It's very highly polarizing. It'll attract the electrons in these bonds enough to weaken the OH bonds enough in the water molecule for water or any other better base to come in and deprotonate it. I don't know if that answered the question or not.
Excellent, thank you for that.
That's
Yeah,
my
no,
version of it. Oh, thanks, Jill. Jill says if you pin my image, it becomes larger. Thank you, Jill.
yeah, I noticed just in time. So thanks. Just as you started to rewrite. No, it's a good point. I hadn't noticed that.
More au fait with Zoom and knows how to do that. I wasn't aware of how to do that, so I've learned something new tonight. Thanks, Jill. That's
That's great. So if you hover over your kind of profile window and the three little ellipses, just click on those. And one of the options is pin. Yeah.
Oh yes, made it big for me as well. Yeah, excellent, good.
Which is useful. Excellent. I think just before that there was just another question about formatting. So when you write the complex of a precipitate, do you need the square brackets when you write the formula?
If it's a complex, then yes, it must have the square brackets, because if you don't put the square brackets around it, you're not necessarily implying it's a complex. So if you're doing a method, if you just wrote that wouldn't score. You've got to have the square brackets round, with obviously the charge outside them, to show that that's not a very square bracket, obviously. Being a bit artistic there, but yeah, no, it's got to have square brackets to be a transition metal. Slightly confusing sometimes, of course. We also use square brackets for concentration, but you can work out which is which by looking at the context of the question, or what you're given, whether it's the concentration of something or whether it's clearly a transition metal complex. We normally have AQ here as well, but you don't always. Remember, you rarely have to put state symbols in for species in A-level exams. Only if RTFQ, if the question tells you to put the state symbol in, or the only time you automatically, of course, do it, and I'm sure you'll all know this, is enthalpy equations. Enthalpy equations must have all the state symbols in.
Excellent. I think so also in terms of formatting, if you're drawing, for example, a tetrahedral complex ion, do you need to add the planar wedges, dashed line, or will the arrows alone suffice?
Ooh,
I suppose that depends.
No, I think it depends what the question's asking. If it's asking you to draw the shape of the complex, then I think you need to show that it's tetrahedral. And if you need to show that it's tetrahedral, I think you need the cheese wedge and the dotted line, as I call it. So if you wanted to draw the copper Cl4 complex, then I would expect to see it something like that. So I'm not drawing my square brackets very well there, so I'm just doing it in a hurry. But I would expect to see that it's tetrahedral in the same way if you were drawing an optical isomer. You would be expected to show the cheese wedge and the dotted line to show that it is tetrahedral. I don't think we'd accept just that, because how's that showing tetrahedral? That's all in a plane. So I think if they're asking you for the shape, to draw the shape, I think you do need the dotted line and the wedge. If it just says do the formula, of course, CuCl4 2 minus, that's not asking you to draw the shape. You don't need to show it. So again, read the question. What's the question asking you for? If it's asking you for the formula, that's fine. If it's asking you to draw the shape, I think you need to show that it is tetrahedral like that.
Yeah, excellent. No, absolutely right. And a nice challenging question for you here now, Peter.
Oh dear.
How does DD splitting work?
Oh dear. Honest answer is I can't remember. I certainly must have done it as part of my. I vaguely remember. I must dig out my undergraduate notes because I've still got them all somewhere. Because when I keep teaching transition metals, I keep remembering what's the Anteller effect. That's something to do with transition metal complexes, but I can't remember what it is. I must go and look it up. I honestly can't remember how it works. I'm going to be really honest. Can't answer that one. You'd never need to know at A level, by the way. Is the cop out answer. But as I'm sure you all know, that's why a lot of the metal ions are coloured, because of course the 3 d orbitals are not all of, in fact, the same energy. They split, and it depends on the ligands. This bit I can remember. Sometimes they'll split, but 3 d orbitals drop to lower energy and 2 go higher. Sometimes it can split the other way round, and it's to do with the different features of the chemistry, the ligands that are involved. I can't remember which does which, and you don't need to know at A level. This is very much sort of undergraduate stuff. But of course, because you've got this energy gap between the orbitals, this energy gap is different, of course, between different ions, depending on what the ligands are coordinated into these. And so that's why it'll absorb different frequencies of visible light. And so, of course, you'll see the complementary color that isn't absorbed. So copper sulfate, so copper iron, copper H2O6 is blue because it's absorbing yellow light. The energy gap corresponds to yellow light. It's absorbing yellow. You see the complementary color, which is blue, and so on and so forth. But I'll be honest, I can't remember how DD splitting works because it's a very long time. I did my degree a very, very, very long time ago. I can't even pass it on to you. I can't pass it on to you, can I, Mark? Because you're not a transition metal chemist either.
I was going to say the answer is that transition metal gets even more interesting at undergraduate level as well.
Absolutely.
So
yes. Make sure you're doing a chemistry degree, then you'll find out. Yes. Or just buy a chemistry text, undergraduate chemistry textbook, read it. Yeah.
Excellent. There are no further questions. If anyone does have a last-minute question, burning question, then please put it in the chat. Otherwise, I'd just like to thank you once again, Peter, for just an excellent discussion afterwards and a really great revision lecture. So thank you so much.
Thank you for coming down to the
if I hand over, I don't know if Jill wants to say a few words. Thanks.
I will. Yes, I'd just like to reiterate from all of us and from all the students, it showed how popular the topic is, that we had the most students we've had for any lecture this year, and I know they really would appreciate it, never mind the time and effort that's gone into and the booklet everybody's received. So thank you very much, Peter.
Welcome.
And as you said, we hope that in a year's time we'll see you, but we'll see you in person. Obviously that won't apply to these students here.
Hopefully not, no.
Hopefully not, but we will look forward to that in another year's time. So I'm sure everybody would like to join with me and say thank you very much. And as you said, we hope they'll do their best and get to the places they're hoping for at university.